Ernest Rutherford's revolutionary proof of the atomic nucleus stands as one of the most transformative moments in the history of science, a discovery that permanently changed the way humanity understands matter itself. To truly appreciate the depth and power of this contribution, one must begin by looking at the scientific world before Rutherford burst onto the scene. In the late 19th and early 20th centuries, scientists believed they already understood the atom fairly well. The most widely accepted model was the plum pudding model proposed by J. Thomson, the discoverer of the electron. According to Thomson, atoms were diffuse, positively charged clouds with negatively charged electrons embedded like raisins in a pudding. This model appeared to make sense because it aligned with known electrical behaviors and seemed to balance positive and negative charges. At that time, atoms were still considered the smallest, indivisible units of matter, a belief inherited from the ancient Greeks. Changing such a deeply entrenched idea would require not just a better theory, but a dramatic, undeniable experiment. Rutherford was exactly the kind of scientist willing to make daring investigations, often guided by intuition and a willingness to question established norms. When Rutherford began experimenting with newly discovered radioactive materials, he quickly realized that alpha particles, tiny, positively charged particles emitted from radioactive decay, could be used as probes to investigate atomic structure. These particles were energetic and heavy, capable of penetrating thin materials. Rutherford had the idea that firing these particles at a piece of matter could reveal how the atoms inside were arranged. His inspiration came from his belief that nature could not possibly be as simple as Thomson's model suggested. If atoms were just uniform balls of charge, then alpha particles should pass through thin materials with almost no disturbance, maybe deflected by tiny angles at most. Still, Rutherford sensed that more complex internal structures might exist, structures hidden from sight and waiting to be uncovered. Together with his young assistants Hans Geiger and Ernest Marsden, Rutherford prepared an experiment using a thin sheet of gold foil, so thin, in fact, that it was only a few atoms deep. They placed detectors around the foil to observe the behavior of alpha particles as they passed through. What they expected was relatively clear. The overwhelming majority of particles would pass straight through the foil with very little deflection. What they observed, however, would shake the foundations of physics. When the experiment began, most of the alpha particles indeed passed through the foil with minimal deviation, as expected. But then came the shocking discovery. A small number of the particles were deflected at angles so large that it seemed impossible. Even more astonishing, some particles bounced directly backward, returning almost to the source. This outcome, as Rutherford famously remarked, was as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back to hit you. The only explanation was that something incredibly dense, small, and positively charged existed inside the atom, something powerful enough to repel heavy alpha particles. This invisible center had to contain most of the atom's mass, since no diffuse cloud of charge could produce such dramatic deflection. Rutherford realized that this tiny, central feature was the nucleus, a compact core holding nearly all the atom's mass and positive charge. This insight was nothing less than a scientific earthquake. It invalidated Thomson's plum pudding model entirely. The atom could not be a uniform sphere of charge. It had to be mostly empty space, with electrons orbiting around a dense nucleus, just as planets orbit the sun. With this single discovery, Rutherford opened the door to the planetary model of the atom, which would later influence Niels Bohr's refinements and eventually evolve into the foundations of quantum mechanics. The implications of Rutherford's discovery were monumental. For the first time, scientists had an accurate picture of atomic structure that went deeper than philosophical speculation. The atom was not the simple building block many had thought it to be. It was a miniature universe with its own architecture and dynamics. Rutherford had provided not only a new model, but also a new method using high-energy particles to probe the unseen world. This approach laid the groundwork for particle physics, nuclear research, and the technologies that would emerge in later decades. By demonstrating that atoms are mostly empty space, Rutherford changed how scientists approached chemistry, physics, and even astronomy. The scale of matter, once thought to be solid and impenetrable, was now known to be far more complex and fascinating. What must also be appreciated is the intellectual courage behind Rutherford's interpretation. Many scientists might have dismissed the strange deflections as experimental errors or anomalies. Overturning an established scientific model is no small feat, especially when that model was proposed by one's own mentor, J. Thomson, yet Rutherford trusted experimental evidence above reputation. He believed that nature speaks through results, not authority. His ability to see beyond expectations and interpret unexpected data is what makes his discovery so remarkable. It was not merely that the nucleus existed, but that Rutherford had the insight and bravery to understand what the data meant and defend his conclusion against skeptics. Rutherford's discovery did more than redefine the atom. It redefined the boundaries of scientific possibility. Within a decade of his nucleus theory, scientists such as Niels Bohr would build the quantum model of electrons orbiting the nucleus in defined energy levels. James Chadwick, working under Rutherford, would discover the neutron in 1932, another monumental step in understanding atomic structure. Each breakthrough became possible because Rutherford proved that the atom was not a single solid entity, but a complex system with deeply hidden components. The nucleus became the center of nuclear physics, a field that continues to uncover the mysteries of matter and energy. Rutherford's revelation of the atomic nucleus also paved the way for nuclear energy and atomic technology. Though he himself would later warn against the dangers of harnessing nuclear power irresponsibly, the reality remains that the world's understanding of nuclear reactions, fission, and fusion all trace back to the nucleus he discovered. When humanity learned how to split the atom, it was possible only because Rutherford had shown where the atom's power lay. Without knowledge of the nucleus, the idea of releasing atomic energy would have remained an impossibility. Another important aspect of Rutherford's discovery is the way it transformed scientific methodology. Before his work, experimentation at the atomic level was largely indirect, based on chemical reactions or electrical behaviors. Rutherford introduced the concept of particle probing, which is still used today in massive particle accelerators like the Large Hadron Collider. The method is simple in concept, yet profound in its implications. By observing how high-energy particles behave when they collide with matter, one can map the internal structure of that matter. This approach has since uncovered quarks, bosons, and countless particles that define modern physics. Rutherford's experiment was the first spark in a chain reaction of discoveries that would expand the known universe far beyond the atom. Rutherford's achievement also illustrates the beauty of simplicity in experimentation. The gold foil experiment required no advanced electronics or massive machinery. It required insight, patience, and the creativity to use available resources in a new way. In an era when laboratories lacked the advanced tools of today, Rutherford relied on careful measurements, visual observation of scintillations, and rigorous analysis. This combination of simplicity and precision created one of the most powerful experiments in the history of science. It shows that even the greatest discoveries often come from the bold use of simple tools. Understanding Rutherford's discovery also requires appreciating the human qualities that made it possible. Rutherford possessed intense curiosity, an instinct for asking the right questions, and an almost playful enthusiasm for experimentation. His personality was a combination of confidence and humility. He did not hesitate to challenge old ideas, yet he always acknowledged the contributions of his colleagues and students. His leadership inspired young scientists to question assumptions and explore daring possibilities. In many ways, Rutherford's discovery of the nucleus reflects his own approach to life, penetrating beyond the surface, searching for the core of every problem, and never accepting easy answers. In addition, his discovery had philosophical implications. For thousands of years, thinkers debated the nature of matter, speculating about invisible particles and their properties. By revealing the nucleus, Rutherford answered a question that had haunted humanity since ancient times. He proved that matter is not solid but structured, not simple but layered. The universe is built from intricate systems all the way down to the smallest scale. This realization transformed not only science, but also our intellectual worldview. Rutherford's revolutionary model of the atom is a testament to how a single discovery can ripple through centuries of scientific progress. His work demonstrated that nature hides its deepest secrets in places invisible to the naked eye, and that revealing these secrets requires courage, creativity, and a willingness to confront unexpected realities. Rutherford's discovery of the nucleus was more than a scientific achievement. It was a turning point in human history, opening pathways to technologies, theories, and investigations that continue to shape modern civilization. By proving the existence of the nucleus, Rutherford gave humanity a new understanding of matter and a powerful tool for exploring the universe. Rutherford's demonstration of the atomic nucleus did not end with the gold foil experiment. In fact, it marked the beginning of a far more profound transformation in scientific thinking. After the initial shock of the results settled in the scientific community, researchers were forced to confront a new reality. Almost everything they thought they knew about atomic structure was fundamentally flawed. Rutherford's announcement was not merely an incremental update to an existing theory. It was the dethronement of the prevailing atomic model and the inauguration of an entirely new scientific era. The atom was no longer a soft, uniform sphere of charge. It was now a dynamic, structured system with a dense center and orbiting electrons, something surprisingly similar to a miniature solar system. This leap in understanding was so revolutionary that it took years for many scientists to fully accept it. But once they did, the revolution could not be undone. The scientific world began to examine the consequences of this newly discovered nucleus. One immediate challenge was explaining how electrons could orbit such a positively charged core without collapsing into it. Classical physics predicted that an electron in orbit would continuously emit radiation and spiral inward, eventually crashing into the nucleus. Clearly, this did not happen because atoms are stable. Rutherford's model raised a major theoretical issue. The atom, as he described it, should not exist according to classical mechanics. This challenge set the stage for Niels Bohr, one of Rutherford's brightest students, to propose a quantum model of the atom just a few years later. Bohr suggested that electrons occupy quantized energy levels, which prevents them from radiating away energy continuously. This was a direct response to the problem introduced by Rutherford's nucleus. Although Bohr's model added new theoretical layers, it was Rutherford's discovery that made the problem visible in the first place. Without the nucleus, there would have been no need for quantum theory to resolve the paradox. While this theoretical revolution unfolded, Rutherford continued to push experimental boundaries. His discovery of the nucleus was not an isolated achievement. It became the core of a career-long effort to uncover the structure of matter. After revealing the nucleus, Rutherford became fascinated with the idea that atomic nuclei themselves might not be indivisible. If atoms were not the simple structures once believed, perhaps nuclei also contained components that could be discovered. Rutherford began to propose the existence of two types of nuclear particles, not only the positively charged protons, but another, neutral particle that might hold the nucleus together. Although he could not prove the existence of the neutron during his lifetime, he anticipated it with remarkable insight. His prediction directly influenced his student James Chadwick, who eventually discovered the neutron in 1932 using experimental techniques rooted in Rutherford's traditions. This discovery filled a major gap in understanding nuclear stability and further solidified Rutherford's legacy as the architect of nuclear science. In the years following the nucleus discovery, Rutherford refined his understanding of nuclear reactions. He began experimenting with the bombardment of atoms using alpha particles, a method that had already transformed scientific knowledge. In 1917, he achieved something previously unimaginable. He became the first person to deliberately split the atom. He bombarded nitrogen gas with alpha particles and observed that oxygen nuclei were being produced in the process. This was the first artificial transmutation of one element into another, a modern version of alchemy grounded in experimental physics. Rutherford's explanation for this transformation relied entirely on the existence of the nucleus. Without the dense core capable of absorbing and reacting to high-energy particles, there would have been no way to change one element into another. The nucleus was not just a theoretical idea. It was a physical system that could be manipulated, broken apart, and reassembled. This insight laid the foundation for nuclear chemistry, nuclear energy, and eventually the chain reactions that define modern physics. As his discoveries expanded, Rutherford became an intellectual leader whose influence reached across continents. His laboratory at Manchester and later at Cambridge became the center of a global scientific movement. Students from around the world traveled to work under him, drawn by his reputation and the revolutionary nature of his research. Rutherford was known for his dynamic personality, quick humor, and ability to inspire confidence. He created an environment in which young scientists were encouraged to think boldly, experiment freely, and challenge established knowledge. Many of the greatest discoveries in early nuclear physics were made by his students working under his guidance. The discovery of the neutron by Chadwick, the development of the Bohr model, and other major breakthroughs were direct outgrowths of Rutherford's mentorship and his foundational discovery of the nucleus. Rutherford's discovery also sparked new questions about the forces that govern the atom. If a dense nucleus existed, what held it together? Why did protons, all positively charged, not repel each other and tear the nucleus apart? This mystery led to the development of the strong nuclear force, a fundamental interaction that holds atomic nuclei together despite the repulsive force of positive charges. Although Rutherford did not discover the strong force himself, his work made its discovery necessary. The existence of the nucleus demanded an explanation, and scientists began searching for the forces that governed its behavior. Thus, The entire field of particle physics was born from Rutherford's revelation. By showing that matter had a deeper, more complex structure, he opened the door to a century of exploration into subatomic particles, quarks, bosons, and the overall fabric of the universe. In addition to reshaping scientific theory, Rutherford's work had profound practical consequences. The understanding of atomic nuclei eventually led to the development of nuclear power and nuclear medicine. Although these technologies emerged long after Rutherford's initial discovery, they would not have been possible without his foundational insights. Nuclear power plants rely on the manipulation of atomic nuclei to release enormous amounts of energy, following the same principles Rutherford helped establish. Similarly, medical imaging technologies such as PET scans and radiation therapy exist because scientists understand how atomic nuclei behave under different conditions. Rutherford's legacy lives on not just in scientific textbooks, but in hospitals, power stations, research laboratories, and countless modern technologies that depend on nuclear science. It is also important to acknowledge the philosophical change that Rutherford's discovery brought to humanity's understanding of the universe. By revealing that atoms are mostly empty space, he introduced a new concept of reality. Matter, to once exp RIE believed to be solid and continuous, was now seen as a collection of particles separated by vast spaces relative to their size. This realization challenged long-held beliefs about the nature of physical objects. It also prompted new lines of inquiry into the nature of space, energy, and the vacuum. If matter was mostly empty space, then what else might the universe contain? What forces operated within these invisible gaps? These questions eventually led to quantum field theory and the exploration of the vacuum as an active, dynamic entity. Rutherford's discovery was not merely scientific. It was deeply philosophical, altering the way humanity perceives the world. Rutherford's influence also extended into the cultural understanding of science. His discovery of the nucleus became a symbol of scientific progress and human ingenuity. It represented a victory of experimental observation over blind assumption, a triumph of daring curiosity over comfortable certainty. In many ways, Rutherford's work became a metaphor for the entire scientific method. It showed that the universe often hides its deepest truths in layers that must be uncovered through courage, creativity, and rigorous testing. The nucleus became a symbol of the hidden core of reality, reminding scientists that beneath every surface lies a deeper mystery. Despite the monumental nature of his work, Rutherford remained grounded and humble throughout his career. He was known for his straightforward manner, his booming laugh, and his lack of pretension. His colleagues often remarked that Rutherford approached science with the enthusiasm of a child discovering a new toy. This attitude contributed greatly to his success. He did not pursue discoveries for fame or recognition. He pursued them out of genuine excitement and a relentless desire to understand the universe. This sincerity allowed him to navigate scientific controversies with grace and confidence. His humility also helped him maintain strong relationships with students and colleagues, many of whom went on to become major scientific figures in their own right. In the final years of his career, Rutherford continued to push scientific boundaries even as the world began to change around him. The rise of political tensions, technological advancements, and the looming threat of global conflict placed new pressures on scientific research. Yet Rutherford remained committed to pure science, believing that knowledge itself was valuable regardless of its applications. He was aware that his discoveries might one day be used for destructive purposes, but he also believed deeply in the potential of science to improve humanity's future. His commitment to truth and understanding remained unwavering, even as the world moved toward an era of profound scientific and political upheaval. Ultimately, Rutherford's discovery of the atomic nucleus stands among the most significant achievements in the history of human knowledge. It represents the moment when humanity first looked inside the atom and saw the true structure of matter. Every major development in nuclear science, quantum physics, and particle theory can trace its roots back to Rutherford's insight. His discovery reshaped scientific theory, transformed technology, inspired generations of researchers, and changed the way humanity understands the universe. The atom was no longer a simple, indivisible particle. It was a structured, dynamic system with its power concentrated at its core. This revelation marked the beginning of modern physics, and Rutherford himself became the father of nuclear science. When reflecting on the full impact of his work, one realizes that Rutherford gave humanity more than just a scientific model. He gave us a new lens through which to view reality. His discovery teaches that even in the smallest, most familiar objects, there are hidden depths waiting to be explored. The nucleus is not just the center of the atom. It is a symbol of the profound mysteries that lie beneath the surface of the world. Rutherford's legacy continues to inspire scientists to look deeper, think bolder, and explore fearlessly. His discovery of the nucleus was not merely a scientific milestone. It was a testament to the limitless potential of human curiosity. The discovery that atoms are mostly empty space was a revelation that changed the course of modern physics, and it emerged from Ernest Rutherford's remarkable gold foil experiment, an experiment so simple in its design yet so profound in its implications that it effectively rewrote the scientific understanding of matter. Before Rutherford's work, the atom was imagined as a compact and uniform structure, something solid and impenetrable. The prevailing theory suggested that atoms consisted of a sphere of positive charge with electrons sprinkled throughout like tiny embedded seeds. In this model, there was no concept of empty space within the atom. Rather, the atom was imagined as a continuous blob of matter. This understanding seemed intuitive, especially because the objects we interact with every day appear solid, firm, and impenetrable. But intuition is not always aligned with the deeper truths of nature, and it took Rutherford's bold experiment to reveal just how misleading this intuition could be. The gold foil experiment began as a simple curiosity. Rutherford wanted to understand how alpha particles, heavy, positively charged particles emitted from radioactive materials, would behave when fired at different substances. What he did not expect was that this examination would become the turning point in atomic theory. Alpha particles were ideal for probing the inside of atoms because they were relatively large compared to electrons and carried enough energy to push through thin materials. Rutherford reasoned that if the plum pudding model of the atom were correct, alpha particles would travel through a thin sheet of gold almost undisturbed. Gold was chosen because it could be hammered into incredibly thin leaves, sometimes just a few atoms thick. This made it perfect for studying how atomic structures might influence the behavior of incoming particles. Rutherford assigned two brilliant researchers, Hans Geiger and Ernest Marsden, to help conduct the experiment. They set up a device in which alpha particles emitted from a radioactive source were directed at the gold foil. Surrounding the foil was a screen coated with zinc sulfide, a material that would produce tiny flashes of light, scintillations, whenever it was struck by an alpha particle. By observing these flashes, the experimenters could track how the alpha particles were being deflected. The setup required meticulous attention, as the scintillations were faint and had to be observed in a dark room with the naked eye. This alone demonstrated the patience and precision of the scientists involved. At first, everything seemed predictable. The majority of the alpha particles passed straight through the gold foil with no noticeable change in direction. This result was consistent with the plum pudding model. If the atom were a diffuse cloud of positive charge, there would be nothing dense enough to significantly alter the path of such heavy particles, yet something unexpected soon emerged. A small percentage of the alpha particles were deflected at noticeable angles, as though they were encountering something solid within the atom. Even more astonishing was the observation that about 1 in 8,000 particles bounced backward, almost directly opposite their original direction. This was an almost impossible outcome if the atom were truly a uniform mass. Rutherford famously remarked that the result was as surprising as firing a cannonball at a piece of tissue paper and having it bounce back. The only explanation that made sense was that the atom must contain a small, incredibly dense center that housed most of its mass. This center, the nucleus, was capable of reversing the trajectory of the heavy alpha particles because it carried a positive charge and was compact enough to resist the particles' momentum. If the nucleus were large, many more alpha particles would have been deflected. The fact that so few were scattered backward indicated that the nucleus occupied an extremely small portion of atom's volume. This realization led Rutherford to conclude something astonishing. The atom is mostly empty space. This insight contradicted thousands of years of assumptions about matter. People had always perceived the physical world as solid. Objects could be held, touched, and felt, and they seemed to occupy continuous space. But Rutherford's experiment showed that these sensations were misleading. The solidity we experience in everyday life comes not from the structure of atoms themselves, but from the interactions between the electric fields of electrons surrounding the nucleus. In reality, the space between the nucleus and electrons is vast compared to the size of the particles themselves. If one imagined the nucleus as a marble placed at the center of a stadium, the electrons would be orbiting far out near the upper seats, and nearly all of the interior would be empty. The gold foil experiment not only revealed that atoms were mostly empty space, but also challenged the belief that scientific discoveries must always conform to common sense. The idea that matter is almost completely empty was so counterintuitive that many scientists initially struggled to accept it. Yet the evidence was clear and reproducible. There was no avoiding the conclusion. The atom was not what humanity had believed it to be. It was not a solid chunk of material, but a miniature system dominated by empty regions separated by tiny, dense particles. This discovery marked the beginning of nuclear physics and reshaped the understanding of everything that exists. One of the most significant consequences of Rutherford's discovery was the need to revise the very language of atomic science. Before the gold foil experiment, scientists talked about atoms as the smallest units of matter, indivisible and fully solid. But Rutherford's results forced the scientific community to acknowledge that atoms had internal structures, components, and dynamics. The atom's interior was no longer a philosophical concept, but a real, physical landscape that could be investigated experimentally. This shift created an entirely new branch of science, nuclear physics, centered on the study of the nucleus and the particles within it. The realization of empty space opened new pathways for understanding radiation, chemical reactions, energy release, and the mechanisms behind atomic stability. Furthermore, the gold foil experiment forced scientists to rethink why matter feels solid if it is mostly empty. Rutherford's explanation came from the interactions between electric charges. When two objects come close to each other, their electrons repel each other, creating the sensation of resistance that we interpret as solidity. This meant that the experience of physical contact is actually the experience of electromagnetic interactions, rather than the touching of solid surfaces. Nothing truly touches at the atomic level. Instead, forces push particles apart. This understanding not only changed physics, but also influenced chemistry, material science, and even philosophical inquiries into the nature of existence. In addition, Rutherford's revelation had profound implications for the development of quantum mechanics. The discovery that electrons orbit a tiny nucleus introduced new questions about how these electrons behave. Classical physics could not explain why electrons did not radiate away energy and collapse into the nucleus. This paradox led directly to the development of quantum theory. Without the knowledge of empty atomic space and a central nucleus, quantum mechanics may not have developed in the same way or at the same pace. Rutherford's work essentially forced scientists to abandon classical models and embrace the probabilistic, non-intuitive nature of quantum physics. The discovery that atoms are mostly empty space also set the stage for the understanding of nuclear energy. Once scientists understood that the nucleus was incredibly dense and contained enormous amounts of energy, the idea of releasing that energy became imaginable. The mass of the nucleus, concentrated in such a small region, implied a powerful binding force holding it together. Breaking or altering the nucleus could release significant energy, as was later demonstrated in nuclear fission. Although Rutherford himself did not believe that nuclear energy could be harnessed on a large scale during his lifetime, he was the first to show where atomic energy resides, not in the space, filled cloud of electrons, but in the compact nucleus at the heart of the atom. What makes Rutherford's discovery even more impressive is the simplicity of the experiment. There were no massive machines, no complex electronics, and no sophisticated computers. It was an experiment of clever design, keen observation, and brilliant interpretation. The most advanced equipment involved was a coated screen that produced faint flashes of light. The experiment required precision and patience, but not advanced technology. This shows that groundbreaking discoveries often depend not on tools, but on the mind using them. Rutherford's genius lay not only in designing the experiment, but in understanding the deeper implications of the results. The gold foil experiment also reveals something profound about scientific progress. Transformative breakthroughs often come from exploring anomalies. Most scientists would have ignored the rare backward deflections as experimental noise, or dismissed them as unimportant. But Rutherford focused on the unexpected, trusting that anomalies often point to deep truths. His willingness to investigate the surprising behavior of alpha particles instead of overlooking it demonstrates his scientific maturity. It illustrates the mindset necessary for true discovery: curiosity, openness to surprise, and a refusal to force observations into preconceived frameworks. Rutherford's conclusion that atoms are mostly empty space revolutionized scientific thinking and transformed the way humanity understands reality. It dismantled classical assumptions, opened new fields of study, and laid the foundation for nearly every major advancement in modern physics. The gold foil experiment was not merely an investigation. It was a revelation, uncovering a hidden truth at the heart of matter. This truth continues to shape scientific research, philosophical thought, and technological innovation in the modern world. When Rutherford first proposed the nuclear model of the atom, many scientists, especially those trained under the Thomson tradition, found it difficult to accept. For decades, the plum pudding model had provided a comfortable explanation: positively charged pudding with electrons embedded like plums. It was simple, symmetrical, elegant, and most importantly, it didn't violate any known laws. Rutherford's model, however, introduced something entirely new: a dense, positive center surrounded by electrons moving in the remaining vast empty space. To many, this felt more like a planetary system than an atom. And because physics demanded mathematical consistency, critics were quick to point out that electrons circling a nucleus, if they truly orbited, should radiate energy and collapse into the nucleus within moments. According to classical physics, Rutherford's atom could not possibly be stable, but this challenge only strengthened the impact of his discovery. A scientific idea does not need to answer every question immediately. It only needs to be powerful enough to transform the direction of inquiry. Rutherford's discovery did exactly that. It forced theorists to rethink the laws governing atomic behavior, pushing physics into the quantum era. How the nuclear model inspired new theories after the gold foil experiment, physicists faced a paradox. Rutherford's atom was physically correct on an experimental basis, but theoretically unstable. According to classical physics, something was missing. This missing piece became the foundation of an entirely new framework of physics. Niels Bohr steps in 1913. Niels Bohr, one of Rutherford's most brilliant students, proposed a refinement that would stabilize the nuclear model. Bohr introduced the idea that electrons could occupy only specific orbits or quantized levels and would not radiate energy while in those stable states. This was more than a fix. It was the birth of quantum theory. Rutherford's insight about the nucleus had ignited this transformation. Without the realization that atoms have tiny, dense centers, Bohr's quantum leaps would have had nowhere to anchor. Rutherford provided the physical structure upon which the future of quantum mechanics could be built. Redefining matter, what it means for reality to be empty. One of the most startling consequences of Rutherford's work was the realization that almost all matter is empty space. If the nucleus were the size of a marble, the nearest electron would be several football fields away. Between them, nothing. For the human mind, which perceives physical reality as solid, stable, and dependable, this was an intellectual earthquake. How could chairs, mountains, buildings, even our bodies, be mostly empty space, yet feel so solid? Rutherford's work forced the world to understand that the solidity of matter is not due to physical substance, but to the electromagnetic forces between atoms. What we perceive as solidity is the resistance of electron clouds and nuclear forces interacting at microscopic levels. Without Rutherford, modern interpretations of matter as fields of forces, not lumps of material, would never have emerged. The role of mathematical verification following Rutherford's discovery, mathematicians and theorists across Europe began developing new tools to analyze the nuclear model. One of the most important figures was Hans Geiger, already closely involved with Rutherford's experiment, whose later work included precise counting of radioactive particles. The need to quantify nuclear behavior inspired new statistical models for radioactive decay, mathematical frameworks for understanding scattering angles, advanced experimental methods for measuring particle interactions. The gold foil experiment did not simply provide experimental evidence. It demanded a new branch of mathematics to make sense of its implications. This was the birth of nuclear physics as a quantitative science, rather than an observational one. The expanding influence across disciplines, the nuclear model of the atom, did not stay confined to physics. Its implications spilled into chemistry, astronomy, material science, engineering, and even philosophy. Chemistry transformed chemists immediately recognized that a nucleus-centered atom could explain why chemical elements behave differently, why atomic weights differ significantly, how isotopes are possible, why energy levels matter in reactions. Rutherford had provided the structural truth. Chemists now had a way to rebuild the periodic table from the inside out. Astrophysics, reborn understanding nuclei, opened the door to eventually understanding stellar energy, nuclear fusion, and the forces powering stars. Without Rutherford, later discoveries such as how hydrogen fuses into helium in the sun would have lacked the conceptual foundation. Material science revolutionized with a deeper understanding of atomic structure. Scientists developed stronger alloys, semiconductors, superconducting materials, nuclear magnetic resonance techniques. Each advancement can trace its roots to Rutherford's insight into the atom's core. The philosophical shockwave beyond the lab, Rutherford's nuclear model, shifted the philosophical understanding of reality. The ancient idea of atoms as tiny, indivisible spheres, stretching back to Greek philosophers, was officially dead. His work implied, atoms have parts. Those parts behave differently from classical objects. The universe is structured from dynamic forces, not solid matter. This challenged centuries of human belief, including the assumption that matter was fundamentally stable and indivisible, changing humanity's ability to unlock energy. While Rutherford did not invent nuclear energy, he laid the foundation that made it inevitable. By uncovering the nucleus and showing that it housed enormous concentrations of mass, he opened the door to understanding nuclear fission, nuclear fusion chain reactions, atomic energy production, nuclear medicine, particle accelerators. Every major scientific or technological development involving the nucleus starts with Rutherford's moment of clarity. His discovery didn't merely help us understand matter. It gave humanity the key to the energy locked within matter. The emergence of nuclear terminology, Rutherford's model also created a new language for science. Terms such as nucleus, nuclear charge, alpha particle, beta particle, scattering angles, nuclear decay, radioactive half-life, became part of scientific vocabulary because of his research. Without this terminology, the later development of nuclear physics would have struggled to progress. Rewriting the atomic model forever, each new piece of evidence forced scientists to look at Rutherford's nuclear model with greater respect. Experiments all over the world, from Germany to America to Japan, attempted to test or disprove his findings. None succeeded. Instead, they kept uncovering deeper layers of truth. The nucleus contains protons, discoveries by Rutherford himself. The nucleus contains neutrons, discoveries by James Chadwick, Rutherford's student. Electrons are arranged in quantized shells. Energy levels determine atomic behavior. These refinements didn't replace Rutherford's model, they amplified it. His was the foundation upon which the skyscraper of modern physics was built. The human element behind the discovery. While science often appears purely rational, driven by numbers and equations, Rutherford's atomic model serves as a reminder of the human spirit behind scientific progress. His personality shaped the outcome. His relentless curiosity pushed him to ask, "What if?" His experimental rigor ensured reliability. His refusal to accept incomplete explanations led to breakthroughs. His leadership inspired his students to expand his discoveries. His humor and energy created a vibrant research environment. It was not only the data, but the man behind the data who created one of the greatest scientific revolutions. How Rutherford's model set the stage for the future once the nucleus was known, the scientific community could turn its attention to questions previously unimaginable. Could the nucleus be broken? What forces bind it? How do radioactive elements transform? What happens when nuclei collide? Is energy stored inside matter? These questions led directly to particle accelerators, nuclear reactors, atomic clocks, radiotherapy, nuclear imaging technology, deep space radiation, research, all because Rutherford had shown that atom was not a simple sphere, but a structured system with immense internal complexity. A permanent legacy in the scientific world today, every chemistry textbook, every physics simulation, every nuclear science curriculum, and every scientific diagram that includes a nucleus owes a debt to Rutherford. His model has been refined but never discarded. His name continues to appear in scientific journals, university lectures, laboratory equipment, research papers, textbooks worldwide. His discovery remains one of the most important turning points in the history of human knowledge. Rutherford's revolution did not end with the realization that atoms contain tiny, dense nuclei. That discovery was only the first step into a far deeper mystery. What is the nucleus made of? If atoms are not indivisible, and if their centers contain concentrated positive charge, then the next question was inescapable. What exactly carries that charge? What is the nucleus built from? No one before Rutherford had a scientifically grounded answer, only vague speculations. The journey to uncover this truth would lead him to another groundbreaking discovery, the proton. This keynote focuses on how Rutherford uncovered the proton, how this discovery reshaped our understanding of atomic structure, and how the identification of the proton turned the nucleus into an intelligible, quantifiable, predictable entity. With this achievement, Rutherford not only split the atom, but also mapped its inner architecture. The logic behind the search before Rutherford's discovery: scientists knew about electrons and knew that atoms were electrically neutral. This meant the nucleus had to contain positive charge equal to the number of electrons around it. But how was that positive charge organized? Was it a continuous blob, a uniform sphere, or were there smaller charged particles inside? Rutherford, driven by his relentless experimental instinct, refused to accept the idea of an undifferentiated positive mass at the center of atoms. He believed nature was more elegant and more structured. His earlier experiments with alpha particles had shown that positive charge is not spread out, it's tightly packed. So he embarked on a systematic effort to uncover the constituents of that charge. Alpha particles, the key to unlocking the nucleus. Rutherford's primary tool for exploring the nucleus was the alpha particle, a tiny, positively charged particle emitted from radioactive substances. He had already used alpha particles to probe the atom's structure in the gold foil experiment. Now he used them as projectiles to strike atomic nuclei directly. Rutherford noticed something remarkable. When alpha particles collided with certain light elements, notably nitrogen, something new was emitted, an unfamiliar particle that behaved differently from the alpha particles he had started with. After repeated experiments, repeated observations, and repeated refinements, he realized that the nucleus was giving off a particle that had the same charge as hydrogen's nucleus. This insight was profound. Hydrogen, the simplest element, contains 1 unit of positive charge, yet here it was emerging from the nucleus of nitrogen. This meant only one thing: hydrogen's nucleus must be a fundamental building block of other nuclei. Elements were not solely unique entities. They were constructed from simpler components. Naming the proton, a new identity for matter in 1917, after careful experimentation and analysis, Rutherford concluded that the hydrogen nucleus is a distinct, fundamental particle inside all atomic nuclei. He named this particle the proton, from the Greek word protos meaning first or primary. It was a fitting name because hydrogen, with a nucleus of only one proton, is indeed the first and simplest element. The discovery of the proton answered several long-standing questions. It explained why elements differ. Different numbers of protons distinguish one element from another. It clarified atomic weights. Heavier atoms contain more protons. It established atomic number as the true identifier of an element. This was a turning point. For centuries, atomic weight had been used to categorize the elements. Rutherford's discovery shifted the focus to atomic number, the count of protons in the nucleus, a system that remains the foundation of modern chemistry. A new order in the periodic table, Rutherford's proton, gave the periodic table a solid, scientific foundation. Instead of arranging elements by weight and guessing why some didn't quite fit, chemists now understood. Hydrogen has 1 proton, helium has 2 lithium, has 3 carbon, has 6 nitrogen, has 7 oxygen, has 8, and so on. This revelation allowed scientists to explain why the periodic table has repeating patterns, because these patterns reflect the underlying structure of the nucleus. Rutherford had transformed chemistry from classification to comprehension. The entire table became a map of nuclear charge. His discovery connected chemistry and physics forever. The proton as the anchor of atomic identity with the proton established. The nucleus was no longer a mysterious lump, but a structured, comprehensible entity. Protons now served as fixed markers defining each atom. They became the unchanging identifiers of matter. A carbon atom is a carbon atom not because of its weight or behavior, but because it has 6 protons. Change the number of protons, and the element itself changes. This led to a profound understanding of nuclear transformations. Radioactivity was not merely atoms breaking apart, but atoms changing identity, forming into new elements by gaining or losing protons. Rutherford's earlier work on radioactive decay was finally connected to a nuclear mechanism. The road to the neutron, Rutherford's discovery of the proton, also highlighted a subtle mystery. Atomic masses didn't match the number of protons. There had to be another particle neutral in charge, but contributing mass. Rutherford predicted this particle and encouraged his students to find it. James Chadwick eventually did in 1932, discovering the neutron, completing the nuclear puzzle Rutherford had assembled piece by piece. The neutron made sense only because the proton had been found first. Without Rutherford, Chadwick's work would have had no theoretical framework. The proton and the future of nuclear science with the proton identified, scientists could begin to explore nuclear reactions deliberately rather than observe them passively. Reaction equations could be written. Nuclear transformations could be controlled. Element creation, once the realm of alchemy, entered real science. This discovery paved the way for nuclear fission, nuclear fusion, particle accelerators, isotope analysis, mass spectrometry, nuclear medicine, astrophysical nucleus. Synthesis models. The proton was not merely a particle. It was a gate into nuclear energy, nuclear forces, and the structure of matter on the deepest level. A legacy of precision and clarity, Rutherford's discovery of the proton brought clarity to the atom. His nuclear model gave science structure. The proton gave it identity. Without this discovery, many of the achievements of 20th century physics, from quantum mechanics to nuclear engineering, would lack their foundations. He turned the nucleus from a theoretical concept into a tangible, measurable, structured system. And with that step, he pushed humanity into the true era of nuclear science. If you want, I can now continue with the fourth keynote, or you can tell me which part you want next. You said, explain a fourth keynote in 1,000 words, ChatGPT said. Here is the explanation of the fourth keynote in 1,000 words, written in the same clear, powerful, documentary-style tone as your previous keynote expansions. Fourth keynote: Rutherford's breakthrough in artificial transmutation, 1,000 words, the first successful transformation of one element into another when Ernest Rutherford achieved the first artificial transmutation of an element. He crossed one of the oldest boundaries in the history of human thought. For centuries, alchemists had dreamed of turning one element into another, lead into gold, base metals into noble ones. But their attempts were rooted in mysticism, intuition, and hope rather than science. Rutherford, with the mind of a physicist and the hands of an experimental craftsman, achieved what the alchemists could not: the transformation of nitrogen into oxygen. This discovery was not chemistry, nor simple radiation. It was the first controlled nuclear reaction in human history. It proved that the atom is neither permanent nor unchangeable. It can be broken, altered, and rebuilt. This keynote explores how Rutherford made this discovery, why it mattered, and how it became the scientific doorway to the nuclear age. The vision that drove transmutation after Rutherford's discovery of the nucleus and later the proton. He was convinced that the nucleus was not an untouchable sphere. It could be struck, disturbed, or even changed if the right force was applied. Natural radioactive decay had already shown that atoms could spontaneously transform into other elements, but this was outside human control. Rutherford asked a new question: if nature can change one element into another, why can't we? This thought, revolutionary for its time, pushed him into one of the greatest experiments in the history of science. Alpha particles as tools, not just observations. Rutherford's earlier studies had shown that alpha particles were powerful, fast, positively charged projectiles capable of penetrating matter. At first, they were used as probes to study atomic structure, especially in the gold foil experiment. But now Rutherford saw another possibility. These particles might be able to strike a nucleus with enough force to knock something out. This was a radical vision, atoms being deliberately broken apart by human hands. To explore this idea, Rutherford did what he always did. He designed a clever experiment. The experiment that changed everything. Rutherford directed a stream of alpha particles at nitrogen gas. Nitrogen was chosen not for mystical reasons, but for its simplicity, availability, and well-understood properties. As alpha particles shot through the nitrogen, detectors registered the products of these collisions. At first, Rutherford observed faint signals that he dismissed as anomalies, but the signals persisted. Something was emerging from the nitrogen chamber, particles that behaved like rapid hydrogen nuclei. This puzzled Rutherford. Why would hydrogen appear in an experiment involving nitrogen? After months of repeated trials, stricter controls, and refined equipment, Rutherford realized the truth. The nitrogen nucleus was being struck by an alpha particle, which caused it to eject a hydrogen nucleus, a proton. The remaining part of the nitrogen nucleus reorganized into a different element, oxygen. In clear terms, nitrogen, 7 protons plus alpha particle, 2 protons right arrow oxygen, 8 protons plus ejected proton. This was the world's first artificially induced nuclear reaction. Rutherford had accomplished the unimaginable. He had changed one element into another through human action. He had split the atom. Why this discovery was revolutionary: the success of artificial transmutation shattered the age-old belief that atoms were eternal and unchangeable. For the first time, humans proved that atomic nuclei could be deliberately manipulated. Elements could be scientifically converted, not by magic, but by physics. The nucleus held immense potential energy that could be unlocked through controlled reactions. This discovery wasn't merely a scientific milestone. It was the foundation of the nuclear age. A controlled nuclear reaction, not an accident. It is important to understand that Rutherford's achievement was not a random event or a lucky observation. It was the result of deep theoretical reasoning about the structure of the nucleus, experimental precision, a clever choice of element and projectile, a mastery of detection techniques. Rutherford understood the rules that governed alpha particle behavior and nuclear charge. It was not alchemy, it was applied nuclear physics. From discovery to interpretation, changing the map of physics, Rutherford's artificial transmutation forced scientists to change their understanding of the nucleus. Before this, the nucleus was seen as a passive entity, something that decayed naturally, but could not be influenced externally. Rutherford proved the opposite. The nucleus could be approached, struck, altered, reassembled. This meant nuclear reactions were not beyond human reach. They could be controlled, studied, and potentially harnessed. This discovery laid the groundwork for nuclear fission, nuclear fusion, particle accelerators, transmutation of elements for research, isotope production in medicine. Every nuclear technology that exists today stands on the shoulders of Rutherford's experiment. The birth of nuclear engineering. Rutherford's transmutation was the first example of a reaction that would later be repeated millions of times in reactors, accelerators, and laboratories around the world. It demonstrated that the nucleus has a structure that can be manipulated with the right tools. This was the intellectual foundation of nuclear engineering. It showed the nucleus could be forced to rearrange, new elements could be produced, energy could be released or absorbed. Nuclear reactions followed predictable laws. Without Rutherford's demonstration, later developments such as controlled fission would have remained theoretical. Philosophical and scientific impact. What made the transmutation experiment extraordinary was not just the scientific result. It was the philosophical message. Rutherford had proven that the building blocks of nature were not fixed statues but dynamic structures. Matter was transformable. The identity of an element was not permanent but dependent on the configuration of protons in the nucleus. This was a turning point in human understanding of the universe. The atom, which had once been considered the uncuttable essence of existence, was now known to be flexible, manipulable, and full of hidden power. A discovery that echoed across generations. Rutherford's artificial transmutation became a cornerstone of 20th century physics. It inspired the development of high-energy particle beams, the discovery of the neutron, Chadwick, the race toward nuclear fission, Hahn, Meitner, the creation of the first particle accelerators, Cockcroft, Walton, modern nuclear medicine, and imaging, the study of the early universe's element formation. Rutherford had not merely discovered something new. He had opened a door that could never be closed. Great scientists make discoveries, but the greatest scientists also create other scientists. Ernest Rutherford was more than a brilliant experimental physicist. He was the architect of an entire scientific generation. His laboratory became a birthplace for ideas, innovations, and future Nobel Prize winners. The fifth keynote explores Rutherford's extraordinary role as a teacher and mentor, and how the people he trained carried forward his vision to shape the future of physics. Rutherford's personal discoveries changed the atom. His students' discoveries changed the world. A leader with a distinct style, those who worked with Rutherford described him as energetic, humorous, impatient with nonsense, and deeply encouraging to anyone with curiosity. His voice boomed through the laboratory. His laughter was famous. He had little patience for bureaucracy and even less for theoretical speculation unsupported by experiment. This attitude shaped his scientific school. He demanded clarity. He demanded evidence. He demanded courage to challenge old ideas. To Rutherford, the laboratory was not a quiet, delicate place. It was messy, lively, and filled with the noise of machinery, detectors, and debates. He created an environment where young scientists felt free to experiment, fail, try again, and eventually succeed. A workshop for future giants, Rutherford did not simply supervise students, he trained them to think independently. Many of the greatest scientists of the 20th century passed through his hands. His laboratory at Manchester, and later at Cambridge's Cavendish Laboratory, became one of the most influential scientific institutions in history. Among his well-known students were Niels Bohr, creator of the Bohr model of the atom; pioneer of quantum theory, James Chadwick, discoverer of the neutron, Hans Geiger Cohen, inventor of the gyro counter, Ernest Marsden, key figure in the gold foil experiment, John Cockcroft and Ernest Walton, first to split the atom using a particle accelerator, George Paget, Thomson Nobel Prize winner for electron diffraction, Mark Oliphant, researcher in nuclear fusion and wartime raid. These scientists did not merely learn from Rutherford. They inherited his boldness, creativity, and passion for experimentation. The Rutherford-Bohr connection, a unique partnership among Rutherford's students. Niels Bohr stands out as a figure who blended Rutherford's nuclear model with quantum theory. Their relationship is a perfect example of how Rutherford mentored. He allowed Bohr to challenge his ideas. He encouraged debate rather than insisting on authority. He never restricted Bohr from exploring new theoretical directions. Rutherford once jokingly said, "Bohr is the only student I've had who is impossible to interrupt." Yet he treasured this quality because it showed depth and conviction. Together, they created a model of the atom that set the foundation for quantum mechanics. James Chadwick, the student who completed the nuclear puzzle, Rutherford long suspected that something besides protons existed inside the nucleus. He often said, "There must be a neutral particle, something that adds mass but not charge." But he could not find it himself. Instead, it was James Chadwick, one of his most trusted assistants, who solved the problem. Working in an environment shaped by Rutherford's philosophy of persistence and creativity, Chadwick discovered the neutron in 1932. This completed the nuclear model that Rutherford had begun, and it earned Chadwick a Nobel Prize. Chadwick always credited Rutherford for teaching him how to design a clean experiment, how to trust measurements, how to think about the nucleus not as an idea, but as a physical object. Thus, the neutron, one of the most important discoveries in science, was a direct result of Rutherford's mentorship. The Cockcroft-Walton achievement, a new way to split the atom. Rutherford's dream was to split the atom using electrical acceleration, not just radioactive decay. He believed that if you could accelerate particles to high energies, you could force nuclear reactions on demand. Two young scientists under his supervision, John Cockcroft and Ernest Walton, made this dream real. Using a high-voltage accelerator built at the Cavendish Laboratory, they split lithium into helium, proving that controlled nuclear reactions could be achieved by human-made machines. This was the practical start of particle accelerators, modern nuclear research, the entire field of high-energy physics. Their success won a Nobel Prize and fulfilled one of Rutherford's lifelong goals. Hans Geiger and the birth of modern detection. No field of nuclear science can exist without detection technology, and this became possible largely because of Hans Geiger, one of Rutherford's closest collaborators. Working with Rutherford, Geiger helped develop techniques to detect individual particles remarkable at a time when such sensitivity seemed impossible. This partnership eventually led to the Geiger counter, an instrument still used today. Rutherford's influence here was profound. He always demanded precise measurement, reproducibility, quantitative analysis. Geiger's devices perfectly reflected this philosophy. The Cavendish culture, a factory of innovation throughout Rutherford's leadership at the Cavendish Laboratory, he cultivated a unique culture, open discussion, freedom to explore shared equipment, joint problem, solving a balance of theory and experiment, daily interaction between senior scientists and beginners. He didn't want isolated researchers working silently in separate rooms. He wanted a scientific community. Many scientists later said the Cavendish felt like a family, where everyone was welcome to think big and attempt bold experiments. This atmosphere was intentionally built by Rutherford. He believed science thrived when ideas were exchanged openly and when young scientists were encouraged rather than intimidated. A legacy reaching beyond physics, Rutherford's mentorship influenced fields far beyond nuclear physics. Electronics, medical imaging, radiation therapy, materials science, atomic clocks, quantum theory, energy research. His students carried his influence across continents, laboratories, universities, and decades. Through them, Rutherford's impact multiplied, forming a scientific lineage that still shapes the modern world. The true measure of his greatness, Rutherford is famous for discovering the nucleus, naming the proton, and achieving artificial transmutation. But perhaps his greatest legacy lies in something more profound: the minds he shaped. He built a generation of scientists who asked deeper questions, embraced experimental courage, challenged accepted truths, pursued precision, believed the atom could be understood through his mentorship. Rutherford ensured that the revolution he began would not end with him. Even today, the methods, tools, and attitudes he taught are embedded in laboratories around the world. His students didn't just extend his work, they created entirely new fields of science. Ernest Rutherford did more than make individual discoveries. He created a scientific discipline. While others studied radioactive phenomena or the atom in isolation, Rutherford brought coherence, focus, and methodology to what became modern nuclear physics. This keynote explores how he transformed fragmented research into an organized, rigorous, and dynamic field of study, and how his vision continues to influence physics today. From curiosity to systematic study, before Rutherford, atomic research was scattered. Radioactivity had been discovered, alpha and beta particles had been observed, and chemists knew some properties of elements. But there was no cohesive framework for understanding the nucleus or nuclear transformations. Scientists observed phenomena, but lacked theoretical guidance and experimental standardization. Rutherford's genius was in seeing the patterns and connecting the dots. He realized that the nucleus had a central role in atomic behavior. Nuclear transformations were governed by measurable forces. Experiments could be systematically designed to test these principles. The behavior of particles could be quantified and modeled. By integrating theory and experiment, he converted scattered observations into a scientific program. Standardizing nuclear experiments, Rutherford insisted on precision, reproducibility, and clarity. His laboratory at the Cavendish was not just a place for experimentation. It was a school of rigor. Students learned that every measurement must be accurate and repeatable. Apparatus had to be reliable and carefully calibrated. Observations must be carefully documented and analyzed. Conclusions had to be supported by evidence, not speculation. This approach transformed nuclear research from a collection of anecdotal reports into a reproducible, credible, and systematic field of study. Modern nuclear physics laboratories still use principles that trace directly back to Rutherford's methodology. The conceptual foundation of nuclear physics through his work, Rutherford laid the intellectual foundation for understanding atomic nuclei. He identified the nucleus as a tiny, dense center of positive charge, introduced the concept of protons as fundamental nuclear components, proposed the existence of neutrons, and inspired their eventual discovery, demonstrated that atoms could be transformed artificially, showed that nuclear forces could be investigated experimentally. Before Rutherford, scientists did not think of atoms as structured systems governed by internal forces. After Rutherford, the nucleus became a concrete entity that could be measured, analyzed, and manipulated. This transformed atomic physics into nuclear physics. Inspiring international research, Rutherford's ideas spread rapidly across Europe and North America. Laboratories in Germany, France, the United States, and Japan began experiments explicitly inspired by his work. Internationally, Rutherford's model served as a conceptual framework. Niels Bohr in Denmark expanded the nuclear model to include quantum orbits. James Chadwick in England discovered the neutron. John Cockcroft and Ernest Walton split the atom with accelerated particles. Frédéric and Iron Joliot, Curie in France, studied artificial radioactivity. Rutherford's influence gave coherence to a field that had previously been fragmented, effectively establishing nuclear physics as a global scientific discipline. Establishing experimental techniques, Rutherford also created the experimental toolkit of nuclear physics. Among his contributions, alpha particle scattering fundamental for probing nuclear structure. Detection methods including scintillation screens, early counters, and careful observation techniques. Radiation analysis separating alpha, beta, and gamma particles. Measurement of nuclear reactions recording energy, trajectory, and identity of ejected particles. These tools became the basis for particle physics experiments and are conceptually similar to methods used in modern accelerators, detectors, and nuclear laboratories worldwide. Defining the scope of nuclear physics, Rutherford did not merely provide tools and data. He defined the questions that the field should explore. Key issues he identified include: how is the nucleus structured? What particles constitute it? How can one measure nuclear charge and mass? How do nuclear reactions occur naturally and artificially? How is energy stored and released within the nucleus? By framing these questions, Rutherford set the research agenda for decades. Every major discovery in nuclear physics, from fission to fusion to particle accelerators, built upon the foundation he created. The concept of artificial nuclear reactions, one of Rutherford's greatest conceptual contributions to nuclear physics, was the idea that nuclear reactions could be induced artificially. Before him, the prevailing view was that nuclear changes occurred only spontaneously through radioactive decay. Rutherford demonstrated, however, that it was possible to manipulate atomic nuclei using alpha particles, particle accelerators, nuclear collisions. This insight laid the groundwork for controlled nuclear experiments, ultimately enabling technologies ranging from nuclear energy to medical isotopes. Integration of theory and experiment. Rutherford exemplified the integration of theoretical insight with experimental practice. He constantly asked, how do the observations fit a model of the nucleus? What predictions can be made and tested? What phenomena have not yet been observed but could exist? This iterative approach hypothesize, test, refine, became the scientific method of nuclear physics. His students, following this approach, carried the field forward, producing results that confirmed, refined, and expanded Rutherford's vision. Training a generation of nuclear physicists, Rutherford's establishment of nuclear physics as a discipline relied not only on his discoveries but also on his mentorship. He trained a generation of scientists who could conduct precise experiments, interpret complex nuclear interactions, build new instruments and accelerators, formulate nuclear models, expand knowledge into chemistry, astrophysics, and particle physics through his students. Rutherford's influence extended well beyond his own work, establishing a scientific lineage that continues today. Impact on modern science and technology. The creation of nuclear physics as a discipline has had profound implications. Energy production, nuclear fission and fusion are only possible because we understand the nucleus. Medicine, nuclear imaging, radiation therapy, and isotopes for diagnosis rely on nuclear physics principles. Material science, isotopic analysis, and atomics, scale engineering require nuclear knowledge. Fundamental physics, the study of subatomic particles, quarks, and fundamental forces, builds on the nuclear model. Without Rutherford's systematic establishment of the field, none of these developments would have been possible with such clarity and consistency. Conclusion: Ernest Rutherford did not merely discover the nucleus, identify the proton, or induce the first artificial nuclear reaction. He created nuclear physics as a coherent, organized, and rigorous discipline. By combining theoretical vision, experimental mastery, and mentorship, he transformed scattered phenomena into a field with methods, questions, and goals. His approach defined what it means to study the nucleus, and his influence reverberates across every branch of physics today. Modern nuclear laboratories, particle accelerators, and research programs are built on the foundations he established. Rutherford showed the world that nuclear physics is not a collection of isolated observations, but a structured field governed by principles, laws, and human ingenuity. In doing so, he left a legacy not only of knowledge, but of a framework for discovery that continues to guide scientists a century later. Redefining the atom. Rutherford's work fundamentally altered our conception of the atom. Before him, the atom was imagined as a solid, indivisible entity, the smallest unit of matter, a plum pudding, where electrons floated within a cloud of positive charge. Rutherford shattered that notion with the gold foil experiment, proving that atoms are mostly empty space with a tiny, dense, positively charged nucleus at the center. This discovery had profound implications. It established the nuclear model of the atom, a model that became the basis for modern chemistry and physics. It revealed that matter is mostly empty space, fundamentally challenging human intuition about the physical world. It laid the groundwork for understanding chemical behavior, atomic interactions, and the mechanisms of radioactivity. By redefining the atom, Rutherford not only changed science, but also reshaped humanity's philosophical understanding of matter itself. Discovery of the proton and the birth of nuclear identity. Rutherford's identification of the proton in 1917 completed the first step toward decoding the nucleus. By showing that hydrogen nuclei are the fundamental building blocks of all atomic nuclei, he provided the scientific explanation for atomic number as the true identifier of elements, the structure and organization of the periodic table, the mechanism behind nuclear transformations. The proton made the nucleus intelligible. Rutherford's insight transformed the nucleus from an abstract concept into a physical, measurable entity. It allowed scientists to think systematically about how atoms combine, change, and release energy, creating the foundation for nuclear energy, quantum theory, and modern particle physics. Artificial transmutation, proving humanity can influence atomic matter. Rutherford's demonstration of artificial transmutation, converting nitrogen into oxygen using alpha particles, was a historic milestone. It proved that atomic nuclei are not immutable and that humans can induce nuclear reactions. This achievement signified the birth of experimental nuclear physics, a bridge between natural radioactivity and controlled nuclear reactions, the first glimpse of the potential to harness nuclear energy. Rutherford's work foreshadowed the nuclear era, including the development of nuclear reactors, medical isotopes, and even the eventual realization of nuclear weapons. He showed that the nucleus, once thought untouchable, could be probed, understood, and altered. Mentorship and the generation of innovators. Rutherford's influence extended far beyond his own experiments. His laboratory became a crucible of innovation, producing some of the most influential scientists of the 20th century. Students such as Niels Bohr, James Chadwick, Ernest Marston, Hans Geiger, John Cockcroft, Ernest Walton, and Mark Oliphant carried forward his ideas, achieving discoveries that built on his foundation. Through mentorship, Rutherford transmitted experimental rigor, the integration of theory and practice, the courage to challenge established ideas, a culture of curiosity and precision. His legacy, therefore, is not only measured in discoveries, but also in the generations of scientists he inspired, ensuring that his influence extended far beyond his own lifetime. Establishing nuclear physics as a discipline, Rutherford transformed nuclear research from a collection of isolated experiments into a coherent scientific field. He did this by standardizing experimental techniques and instruments, defining the key questions about nuclear structure and reactions, integrating theoretical insight with careful observation, encouraging international collaboration and scientific discourse. As a result, nuclear physics became an organized, systematic discipline capable of producing repeatable, reliable, and transformative results. Laboratories worldwide adopted his methods and expanded upon them, creating the modern global community of nuclear science. Influence on quantum mechanics. Rutherford's discoveries directly influenced the development of quantum mechanics. By establishing that atoms consist of a dense nucleus surrounded by electrons, he provided the experimental evidence that inspired Niels Bohr to develop the Bohr model of the atom, introducing quantized electron orbits. This work led directly to the broader field of quantum theory, explaining phenomena such as atomic spectra, electron transitions, energy quantization, chemical bonding at a fundamental level. Without Rutherford's nuclear model, the theoretical leap to quantum mechanics might have been delayed or taken a different trajectory. His work bridged classical physics and the emerging quantum framework. Shaping modern science and technology, Rutherford's discoveries and methodologies laid the foundation for countless modern technologies. Nuclear energy. Understanding the nucleus allows controlled fission and fusion reactions, medical applications, radiation therapy, nuclear imaging, and isotopic tracers. Particle physics, accelerators, and detectors are based on principles he pioneered. Materials science, isotopic analysis, and nuclear techniques inform advanced engineering. Astrophysics. Nuclear processes explain stellar energy, nucleosynthesis, and cosmic radiation. His influence extends across disciplines, shaping both theoretical understanding and practical applications. Rutherford's philosophical and cultural impact beyond science. Rutherford's work reshaped human perception of reality. By showing that matter is mostly empty space and that atoms are dynamic rather than permanent, He challenged centuries-old assumptions. His discoveries blurred the line between the tangible world and the underlying forces governing it. He inspired philosophical inquiry into the nature of matter and existence, scientific curiosity about unseen forces and energies, a cultural understanding of humanity's ability to explore and manipulate the universe. Rutherford's discoveries reinforced the idea that humans are capable of uncovering profound truths hidden in nature, even if they contradict everyday intuition. Recognition and enduring fame. Rutherford's contributions were widely recognized during his lifetime. He received numerous awards, including the Nobel Prize in Chemistry, 1908, for his work on radioactive substances, election to prestigious scientific societies, worldwide honorary degrees, and international acclaim. More importantly, his reputation has endured. He is celebrated not just for isolated discoveries, but for his holistic transformation of science, mentorship, and ability to inspire future generations. Conclusion: a legacy that transcends time. Ernest Rutherford's seventh keynote, the enduring legacy of his work, is more than a summary of achievements. It reflects the profound and lasting influence he had on science, technology, and human understanding. He redefined the atom, discovered the proton, demonstrated artificial transmutation, mentored generations of pioneering scientists, established nuclear physics as a rigorous discipline, influenced quantum mechanics and the study of matter, laid the foundation for modern technology and nuclear energy. Rutherford's vision, methodology, and discoveries created a roadmap that scientists continue to follow. His legacy is not limited to laboratories and textbooks. It is embedded in the very way humanity studies, manipulates, and comprehends the universe. He did not just split the atom. He split open the boundaries of human knowledge, showing that the deepest mysteries of matter can be explored, understood, and harnessed. In this sense, Rutherford's true achievement is eternal. He made the invisible visible, the incomprehensible comprehensible, and the impossible a challenge that human ingenuity could overcome.